Right, so you want your notebook out with the notes for 2.5. You can fill this in as we go here. We're going to look at implicit differentiation. So far, all of the problems that we have dealt with have been finding the derivative or differentiating explicitly, which just means that the equation is solved for y. So if you look at this first example here in explicit form, y equals 3x squared minus 5, all of our equations were solved for y. You said the derivative of y with respect to x then would be 6x. And we wrote it in this form y prime. There is another form also that we didn't really use that looks like this, dy over dx, which just means the derivative of y with respect to x. It means the same thing as y prime or f prime of x. You may have an equation, though, that's not solved for y, like this one, xy equals 5. But that one's not too difficult to put it from implicit form, where it's not solved for y, into explicit form, which is solved for y. If you divide both sides by x, and maybe write that 5 over x as 5x to the negative 1, now you can take the derivative of that using your power rule. You'll have negative 5x to the negative 2, and then you can put that x to the negative 2 at the bottom, make it a positive x squared. So then, if you continue this example, to try to solve this equation for y, it's going to be extremely difficult to do that. I'm not really sure what you'd have to do. I'm guessing you'd have to complete the cube in order to get that y term by itself. Which I have no idea how to do. So we have a different way that we can go through and find the derivative when it's in implicit form, and it's not that awful. So remember, d over dx just means this isn't an equation. It's just one single term. So I'm trying to find the derivative with respect to x. So the derivative of x cubed, 3x squared. If I use this dy over dx notation, I'm going to come back to that. We would have, I took the derivative of x with respect to x. We could put dx over dx with it. We never bothered to write that because dx over dx would just be equal to 1. So we never bothered with that notation. We just say the derivative is 3x squared. So we'll come back to that if you're not sure what I'm talking about there. Let's look at the next couple here. So now we're looking for the derivative of y to the 5th. We're taking the y with respect to x. So I don't have an x as a variable, but they want me to take the derivative with respect to x. So you take the derivative just the way you did before. Using power rule, you'll have 5y to the 4th. But what I need to do is I need to multiply by something that says I took the derivative of y with respect to x. So anytime you take the derivative of a variable that's not an x, and you're taking the derivative with respect to x, you'll have dy over dx with it. If your variable was a z, you would have dz over dx with it. Just depends what the other variable is. So the derivative is the same thing. If you have any variables that are not an x, you'll put a dy over dx with it. So this next one here, derivative of 2x would be 2. Derivative of 7y squared would be 14y. I took the derivative of something that was an x, so I need dy over dx just with that term there. All right, and all the rules that you had before still apply. So this is two functions in the next example here multiplied together. So we need to use a product rule for that. So if I take the derivative of this one, it would be the first function times the derivative of the second. Derivative of y squared would be 2y. It's not an x, so I need dy over dx with it. Plus the second function, which is y squared, times the derivative of the first, which is 1. So if I wanted to put for the derivative of 1, I could put dx over dx with it, but we don't bother to write that because you just multiply them by 1. And then you can simplify this a little bit. Dy over dx plus y squared. But now most of the problems that we've looked at were not just single terms that you were taking the derivative of. They were entire equations or functions that you were taking the derivative of. So it was set equal to something. So let's look at a problem where it's set equal to either another variable or a numerical value, something to that effect. Hold on a minute. There we go. All right. So we're looking for implicit differentiation for an equation that's in implicit form. So our strategy is that we're going to first differentiate both sides of the equation with respect to x. So take the derivative of both sides of the equation. We're going to get all of the terms that have dy over dx together on one side. And we're going to put all the other terms on the other side. We can factor out the dy over dx, and then finally solve for dy over dx. It sounds like a lot of steps. So we'll start with taking the derivative. Hold on 1 second, I just got to close this out. There we go. All right, so if I take the derivative of y cubed, I'm going to have 3y squared. I took the derivative of something that wasn't an x, so I need to put dy over dx with it, and it's multiplied. Plus, my second term is y squared, so the derivative of y squared is 2y. That arrow out of the way. Dy over dx, because it was not an x I took the derivative of. Minus 5y, so the derivative would be minus 5. Dy over dx. Minus x squared, derivative of x squared would be 2x. I could put dx over dx with it, but that's just equal to 1, so I'm just going to leave it as 2x. And then the derivative of negative 4 is 0. So I'm going to put all the terms that have dy over dx on the left side. Everything else on the right-hand side. And you'll be able to combine some of these steps together here. I can factor out this common factor of dy over dx. I'm left with that 3y squared plus 2y minus 5. And then I can divide by what's in the parentheses there. So I have my derivative. Dy over dx means the derivative. Now, if you look at this derivative, you're going to notice that what's different from the other derivatives that you've had so far is this derivative has both x's and y's in the derivative. And that's fine. You don't have to try to solve for y or anything. Just leave it that way. The next example, we'll do this one on Tuesday. We're going to have to find the slope for the tangent line. So when I have my derivative, instead of just plugging in values for x, I'll plug in values for both x and for y. So we'll do that one on Monday. The last two problems that you have in the homework, if you flip to the example 8, this is the last type that you will see. So the last two problems in your homework, they want you to find d2y over dx squared. Fancy way of saying second derivative. All right, we use double prime because we were looking at y prime. So y double prime would be the second derivative, or f prime and f double prime. So d2y over dx squared would be, if I have dy over dx, the next derivative would be d2y over dx squared. So we're going to find the derivative. So let's find the first derivative first. So derivative of x squared would be 2x. Derivative of y squared would be 2y. I just took the derivative of something not x, so I need dy over dx with it. And derivative of 36 is 0. And I'm going to get that dy over dx by itself. I'm going to put this 2y on the right side. And then if I divide both sides by 2y, I'm going to have my derivative dy over dx. These 2's will cancel. I'll have x over y. So there's my first derivative. Now I need to find the second derivative. And to find the second derivative, I need to take the derivative of the first derivative. So I would say that dy over dx, so second derivative would be d2y over dx squared. And the derivative for x over y, I could do quotient rule or I can do product rule. I'm going to do quotient rule. This one's not too awful. So bottom function times derivative of the top, derivative of x is 1, minus the top function, which is x, times the derivative of the bottom. Derivative of y is just 1, but it's not an x, so I need a dy over dx. And you could write this 1 or not write that 1. It's all good. And then it's all over the bottom squared. So I have y minus x dy over dx all over y squared. Now that looks pretty clunky. There's something else that we can do with this. If you look back, we know what dy over dx is equal to. It's equal to x over y. So in this derivative, I'm going to take out dy over dx, and I'm going to replace it with what dy over dx is equal to in terms of x's and y's. And then I can simplify this. I have y minus x squared over y divided by y squared. Complex fraction, if I multiply top and bottom by y, I'll have y squared minus x squared in the top, and I'll have y cubed in the bottom. So this answer is good. You won't see this in the back of the book. They'll do a little bit more simplification. If you go back to the original problem here, I have x squared minus y squared equals 36. If I rearrange that, I'll have negative 36 equals y squared minus x squared. So what they'll do is they'll take this y squared minus x squared out of the top and replace it with negative 36 over y cubed. Think about it, if you had to plug numbers in, it would be easier to plug numbers into this answer where you only have one variable to work with instead of that top one where you have two variables and you have the difference in the numerator there. So you'll see a couple problems like that, the last two problems for the homework. So that's it for implicit differentiation. We'll do a little bit more on Tuesday, and you'll be all set.